with what looks like two ethane groups attached to it. Right? Or in this case, the ethane groups are combined. Alright, okay, good. So from the organic perspective, I don't really care about all of the our balancing equation. The way I would write this, in fact, is just say Rx in the presence of with lithium in the presence of dry ether would give rise to RLi. Organic chemists tend not to worry about the inorganic products. Okay, now this is a base. It's electron rich. We learned, and we did this when we looked at acid-base chemistry a couple lectures ago. If I treat this species now with H2O, D2O, or T2O, it'll give rise to RD, RH, or RT. And the logic here is actually quite simple. The R minus is basic. The H's attached to O are acidic. So if it's an H attached to O, or a D attached to O, whatever, there's a delta plus charge here because the O is electronegative. So there's a delta plus charge here. My R in my alkylithium, oh sorry, I didn't write that down. These compounds are called alkyl lithiums. Again, organic chemists have no imagination when it comes to naming. It's an alkyl group attached to a lithium. What do we call it? An alkyl lithium. The alkyl lithium, the R in the alkyl lithium is electron rich. So it's not surprising it's going to attack the electron poor species. That bond will break, and I will end up with RH. I'll end up with lithium plus, and then essentially OH minus. Okay? And then other stuff will happen down the road. So, or you know, from a simple-minded perspective, you can kind of think of it as if it were R minus attacking the water to give rise to RH. And then you lose OH minus. And I'm going to draw this in quotation marks because it's not really R minus. It's R delta minus, right? So I don't want to say it's R minus. But it's a simple acid-base reaction. So I can introduce a label from the organometalls, from the haloalkane, either directly by zinc acid reduction, or I can take the haloalkane, convert it into the alkyl lithium, and then treat the alkyl lithium with water if I wanted to just make the alkane, or use the opportunity to introduce a label, D or T. Again, any compound that H can form, D can form, and T can form. So, for example, maybe I didn't mention this up here, but with the zinc acid reduction, how do I make H3O+? And the answer is I'll dissolve HCl or H2SO4 in H2O, and that gives me H3O+. If I want to make D3O+, I'll dissolve DCl or D2SO4 in D2O, and that gives me D3O+. Right? If I want to make T3O+, I'll dissolve TCl, T2SO4 in T2O, and make T3O+. Anything H can do, D can do, and T can do. The only issue is because D and T are so rare, they're very expensive. So if you want to do chemistry to put in tritiums or deuterium, you pay through the nose for it. It's actually quite expensive. Right. So I can make the organometallic. I can make the alkane by hydrogenation of alkenes or alkynes using heterogeneous catalysis. Syn addition for alkenes, which we will come back to later on. There's a little nuance we're going to talk about. I can make alkanes from haloalkanes by two methods so far. One is by zinc acid reduction, and the other then is via the organometallic. And the organometallic we've used in this case is lithium. I don't want you to think that the only organometallic that we have access to is the alkyl lithium. We can do this if I take Rx, I can treat Rx with magnesium in dry ether, sodium in dry ether, or, as I've done here, lithium in dry ether. This gives the alkyl lithium, this gives the alkyl sodium, and now both of these are monovalent metals. Here, because the magnesium is divalent, what you get is RMgX. This is called a Grignard reagent. This is called an alkyl sodium. And you've seen already, this is called an alkyl lithium. And those are the three most common of the organometallics that we will meet in the organic 1 and organic 2 series. There are a couple of others we meet in organic 2. These are all we will meet in organic 1. And you want to let go of the notion that metals can't form covalent bonds. Metals can form covalent bonds. Now, I will just get into it here. The alkyl lithium, this bond is covalent. The Grignard, the RMG bond, is covalent. The RNA is actually composed of ions. So there's an R minus and an Na plus. So this is actually an ionic compound. So this is covalent, although highly polar. This is covalent, highly polar. This is actually ionic, because sodium is a lot more electropositive than lithium or magnesium. In fact, if you look at the periodic table, lithium and magnesium have that diagonal relationship, which is why their chemistries tend to be so similar. I set a timer. Can't have but a couple more minutes. So there's another method of preparing alkanes from haloalkanes. And this is called the Corey-Posner-Whiteside-House reaction. So C would be the Corey-Posner-Whiteside's house reaction. Just a few notes here. Corey, this is E.J. Corey, Elias J. Corey. Corey won the Nobel Prize in Chemistry in 1998, I think. And he won it really for a massive volume of really good work. Corey's at Harvard, for instance. Harvard, I think, not Princeton. One of the Ivy Leagues. Harvard, I think, not Harvard. In his group, in his research group at Harvard, Corey had graduate students and postdocs named Posner, Whiteside-House. Posner is Gary Posner. And Gary Posner was a really just very bright, very personable, really a great guy who got his PhD under Corey and then went to Johns Hopkins in the 80s and started a really rich career. Did a lot of work in organic synthesis, a lot of copper-mediated chemistry, synthesizing a wealth of anti-malaria drugs for the US military. He's a really brilliant guy, and really very humble, very wonderful guy. I had the pleasure of taking a course in organic synthesis from Gary. He passed away a couple of years ago, which is, I think, a great loss, really great loss to the organic, the chemistry community, broadly defined. But he is memorialized by his contribution to organic chemistry in devising a wonderful synthetic method for carrying out alkane preparation. So how does this work, and why is the Corey-Posner-Whitehead-House reaction, why is it important? Well, if you look at what we've done so far, we took an alkene or an alkyne that had, I don't know, let's say some number of carbons. 5 carbon, well, we started with 4. So I would take a 4-carbon alkene or 4-carbon alkyne, and I'd make a 4-carbon alkane. The number of carbons didn't change, right? So if you remember, we might have taken, I think we took, seriously, wow. Yeah, that actually got it. So we took a 4-carbon alkene or a 4-carbon alkyne. You probably cannot see that. It's not really very clear. Curious. So we took a 4-carbon alkene or a 4-carbon alkyne, or we took a 4-carbon haloalkane and we converted them into the 4-carbon product. This might have been zinc and H3O+, or it could have been 1 lithium and dry ether, followed by H2O. This would have been hydrogen gas and platinum. This would have been 2 equivalents of hydrogen gas and palladium. Okay? But 4 carbons, 4 carbons. So we were making an alkane with the same number of carbons as the substrate. Okay. What the Corey-Posner-Whitehead-House reaction allows us to do is to build what we call higher alkanes. In other words, alkanes with more carbons, which is a huge deal for a number of reasons. The one I'm going to talk about now, just very quickly, because is that, and we've talked about this chart a little bit before. When you look at organic synthesis, and this is a brief introduction into it. When you look at organic synthesis, the various steps involved in a synthetic reaction fall into 3 classes. Either we are doing redox. So for example, going from here to here is a redox reaction. We are doing functional group interconversion. So we're changing from a haloalkane to an alkane. Or we're doing carbon-carbon bond formation, or breakage. Reactions in which we make or break carbon-carbon bonds essentially represent 1/3, it's one leg of a tripod, right, in organic synthesis. These are huge reactions. And what the Corey-Posner-Whitehead-House reaction does is allow us to make carbon-carbon bonds. So it's a pivotal reaction. It contributed to the volume of work that led Corey to get the Nobel Prize. Okay, so time is a little short, so I won't start that, but I'll tell you a little story. After Corey won the Nobel Prize, and I'm pretty sure it was 1998, you could Google it. Gary invited him to come to Hopkins, so I did my PhD at Hopkins. Gary invited him to come to Hopkins and give a lecture. And of course, Hopkins has had its share of Nobel laureates. But Corey came, gave really just a very brilliant lecture to all of the chemistry faculty members, and it was a pretty big department all of the grad students, many of the undergrads were in the audience. But what was funny, that's my alarm, what was funny is that one of the things that when you sit in a seminar, particularly at that level, whether people want to admit it or not, is, you know, once people put structures on the board or on the monitor, the audience leans in looking for errors. And that sounds really bad and vicious, but it's what people do at that level. And you know, Corey had put some structures up and was showing some mechanisms, and you could feel the audience lean in. And Corey said something which to this day I find just incredible. He said to the audience of, you know, I mean, this is Johns Hopkins. He said to the audience, don't bother to look for errors. There aren't any. And you felt the audience go, and the air kind of left the room. But it was an incredibly confident thing to say to chemistry faculty at Johns Hopkins. But it was great. Gary Posner, I mentioned, I took a class from him. You know, he really just a wonderful, wonderful guy. Great chemist, great contribution to the discipline. I think he would be sorely missed by those who knew it. So we'll stop here and pick up from here on the next lecture. Okay, thank you guys.